Welcome back, my friends, to the Actual Academy. This is Dr. Me. We will now solve a confidence interval problem involving sigma. So we have a random sample of size n is equal to 18 from a normal distribution with a sample standard deviation of s is equal to 5.1, and we'd like to construct a 95% confidence interval for sigma. Okay, this is a little different. Typically we solve confidence intervals for population means, but here we're requesting a confidence interval for a different population parameter, namely the the population standard deviation, sigma. So in order to do this, we need to review this fact here that's very important. If we do have data IID, independent and identically distributed, from a normal distribution with mean mu and variance sigma squared, then it turns out that this quantity here, n minus 1 times s squared divided by sigma squared, is distributed as a chi-square distribution with n minus 1 degrees of freedom, where n is the sample size that we generate from the normal distribution. So I'd like to actually derive the confidence interval for sigma. It follows that this random quantity here, since it is distributed as a chi-square distribution with n minus degrees of freedom, that the probability that is between these critical points of the chi-square distribution, as chi-square of 0.975 n minus 1 degrees of freedom and a chi-square of 0.025 n minus 1 degrees of freedom, is equal to 0.95. So this is actually called a pivotal quantity here, this term in the middle, in that the distribution of this is independent of what we're actually trying to find the confidence interval of, and that's sigma squared. So this can be inverted, so to speak, using algebra, and that's exactly what we'll do next, and literally solve for sigma squared in this expression here. And I will assume that you know how to find these values, the chi-squares values here, from a chi-square table. We'll actually produce them here, but we won't actually run through the exercise of finding what they are on a table. So this statement is true because of fact, and it follows that since this is true, using algebra, we can isolate sigma squared, and this essentially is going to give us our confidence interval because we've isolated sigma squared. So just as a quick refresher on the chi-square table, just to make sure you understand what these values are. If you do look at the chi-square distribution, it looks like this. Okay, so this is our chi-square distribution with, say, some n minus 1 degrees of freedom. Then if we want to look at the area under the curve to the right of this value, this is what we're calling chi-squared of, say, of alpha, again with n minus 1 degrees of freedom. So this would be our alpha here. So if we want to look up these values here, which I've already done, and I trust you to look these up yourself. If we want to look up chi-square 0.025 with 17 degrees of freedom, because n is equal to 18, so we subtract 1 to get 17 degrees of freedom. This is actually equal to 30.191, and chi-squared of 0.975 is equal to 7.564. Continuing on, because we'll need that data in a moment, we had this probability statement based on the fact, which implied this probability statement, which now implies this probability statement. So all we've done is just isolated or solve for sigma here by taking the square root, which is a legal step, and that gives us then our 95% confidence interval for sigma. So this statement here is precisely saying that is a 95% confidence interval for sigma. So using the data we have here, I will actually numerically compute what the confidence interval is for sigma. And if you don't mind, I'm actually going to use this space right here and write the final answer that I generated using Excel. And again, I'm just plugging in 17 for n minus 1, s squared. I plugged in 5.1 squared, and then we have our critical values for the chi-square given here. So when all the smoke clears, the confidence interval I get numerically for this problem is 3.827, and I think this is rounded. That's the lower limit for sigma, and then the upper limit is 7.646, and that's our confidence interval. Excuse me. And confidence intervals are written like this, with a comma in between two numbers and then parentheses at the ends. And again, this is a 95% confidence interval for sigma. Thank you very much.